Okay, welcome back. What we're headed towards is essentially graphing functions without our graphing calculators. You may remember in pre-calculus worrying about graphing polynomials. Okay? And we had a similar issue there, in particular, the polynomial, you could tell the end behavior based off the degree and the leading coefficient. So recall if you had some sort of polynomial like f of x equals negative 3x to the fourth plus 2x squared plus 1. The degree is even. The degree, which equals 4, is even. The leading coefficient, I'll just say LC, is negative 3, which is less than 0. And in that case, you could say its end behavior was kind of like a parabola. You know, it's a sad face. So it goes down in that direction and down in this direction. And then there's some business in between. I don't really know. Okay? All right. So also then, if your leading coefficient was positive, you had stuff like 3x to the fourth plus 2x squared minus 1. So the degree here is 4, is even. The leading coefficient is positive. It's 3. It's greater than 0. So in that case, it's a happy face. And I don't know what happens in between. Right? For odd functions, then f of x, maybe negative 2x cubed plus 1. And the degree is odd, leading coefficient is negative, so you'd have this behavior on the ends. And then for something like f of x equaling positive 5x to the fifth, maybe, its behavior on the ends would be the sort of flipped version of the previous. Right? So it would look like that. Okay. From there, you probably talked about the end behavior of rational functions. Right? So if you have a rational function, we just call it r of x maybe, r of x, which is a ratio of two polynomial functions, say f of x and g of x, or maybe even p of x and I don't know, whatever value. So assuming that these are two polynomials, you could tell kind of its behavior as well in the long run. So if the degree of the denominator, or rather, let's go with the degree of the numerator, which is f of x, was greater than the degree of the denominator, it would just keep on going up and up and up. Usually they have like they call it a slant asymptote, right? But it would be going up and up and up in the long run. It would just keep on going up. So in this particular circumstance, they'd be talking about asymptotes, right? We're talking more now about infinite limits. What happens as x gets really, really big or x gets really, really small? So yeah, we're interested in this object, the limit as x goes to infinity of our function, or the limit as x goes to negative infinity of our function. Okay. But back in the day, in pre-calculus, you thought of this as horizontal asymptotes. Okay. So back in the day, you would have said if f of x was greater than the degree of g of x, it doesn't have a horizontal asymptote. So no HA, but it would have had maybe a slant asymptote, right? For us, what does that mean for now? It means the limit as x goes to infinity of our rational function is either plus infinity or minus infinity, to be determined. Right? So it's one of those. The other case is r of x equaling f of x over g of x. So we had this case if the degree of f of x is actually less than the degree of g of x, the horizontal asymptote would have been just x equals 0, or rather y equals 0. Okay? So in calcland now we'll say the limit as x goes to infinity of r of x, that's equal to 0. Okay? Then the other case where the degree of the numerator and denominator were equal, if r of x equaled f of x over g of x, two polynomials, and the degree of f of x equal the degree of g of x, the asymptote, the horizontal asymptote, would then be y equals the leading degrees, the leading coefficients of the particular polynomials, right? So now in our setting, the limit of r of x as x goes to infinity or negative infinity will be the same deal. It will just be a sub n over b sub n. Okay, so connecting what we're doing now to what you've done in pre-calculus, it's about those horizontal asymptotes. It's about the end behavior of a graph. Okay, so we could even talk about limits in this setting. The limit of 3x to the fourth plus 2x squared minus 1 as x goes to positive infinity is just going to be infinity. It'll just go up and up and up and up. Okay? And then the negative version going in the other direction, it's also going to go to positive infinity. Okay, so I guess it's just a way of describing end behavior of these graphs, and that'll help us once we get to graphing these things, and that's what 4.6 will be all about, graphing. Okay. So anyways, in the book, then this is section 4.5, limits at infinity. In the book, what we're talking about is, well, they begin you, and it's end behavior again. We're talking about end behavior of a particular function. You can start out just by looking at charts, right? So limit as x goes to infinity. So as x goes in this direction, what happens to the y values of the graph is really what this is asking about. You can do a table of values, so x, y, and you just pick values of x that are going to infinity. So maybe do a sequence, 10, 100, 1,000, etc. Okay. So if you plug those values into this function and look at the outputs, you get an idea where it's going. Okay. In the particular case, we'll have 2.26, 2.03, 2.003, and then 2.0003. So it seems like this is going to 2, and that would be the case. And if you think about our previous discussion, it's the third case. The degree of the numerator is 1, the degree of the denominator is 1. So our limit as x goes to infinity is just the ratio of the leading coefficients. 4 divided by 2 is 2. Okay, that's no coincidence. You could also do this in the negative direction, so the limit as x goes to the negative infinity of this function. So we do a numerical investigation with a chart. Again, I'll pick values going to negative infinity, this time negative 10, negative 100, negative 1,000. Okay. Plot those into my formula, and I get numbers like 1.76, 1.975, 1.9975, then 1.99975. So it looks like it's getting really, really close to 2 again. And that's the case. Okay. So if nothing else, hopefully you can finagle a numerical example to figure out your limit. In the long term, you want to be able to look at these and just know. Okay? So some of the topics later on when we're dealing with sequences and doing in Calc 2, you'll be expected to just know these by looking at them. So these kind of limits are very, very common. There's a strict definition here, of course. If you want to become a math major, you're going to have these type of things memorized. And basically, part 1, the limit as x goes to infinity of f of x equaling L means that for any epsilon greater than 0, there exists this time a number m greater than 0 such that when x is greater than m, then the distance between f of x and L will be less than that particular epsilon. Okay. Likewise, too, the limit as x goes to negative infinity of f of x equaling L means that for any epsilon supplied, there exists an n this time greater than 0 such that, and we're talking about going in this other direction, so if x is less than that m value, then the distance between f of x and L will be very small. Okay, so that's the deal. We won't go into these. If, like I said, you keep taking math classes, you're going to want more and more proofs from you, especially if you're a math major. They'll want you to have these kind of forms memorized. We, in this class, so I won't be punishing you in that fashion. Not that that's a punishment. I shouldn't say that. We won't be going into that kind of detail. Okay. Okay, anyways, you know, end behavior, it's really just a matter of horizontal asymptotes. And we say that the line y equals L is a horizontal asymptote. If the limit as x goes to infinity of f of x equals L, or the reverse direction, the limit as x goes to negative infinity of f of x equals L. Sorry, that ran off the page. The point of this is you can have more than one horizontal asymptote. You can have it going to one value in one direction and a different value in the other. Likewise, you know, this thing may not have a horizontal asymptote, and you saw those in your pre-calculus classes. Okay, so maybe there's a slant asymptote or something of that effect. Okay. So limits. The usual limit laws will apply here. So if you already know how to do limits from our previous chapter, you're going to be pretty good here. Okay, so the limits, the usual rules apply. In this new context, there are some particular limits we want to pay particular attention to. Note if you have the limit as x goes to infinity of 1 all over x to pretty much any positive power, like x to the 5th, this thing will go to 0. Okay? And also, if you have something like the limit as x goes to negative infinity, all over of 1 all over x to the I don't know, negative 5th, that will also, well, this will not equal 0. This will go to infinity. But if you have, sorry, yeah, this has to be positive. Okay, sorry. So if you're plugging negative values into here, this will also go to 0. Okay, is the point I'm trying to make. Whether you have 1 over a million or 1 over a negative million, it's both examples are close to 0. It's just you're approaching from either one direction or the other. You're approaching 0 from one direction or the other. Okay, so some other ones then. The limit of e to the x as x goes to negative infinity is 0. And you can tell that by the graph. Remember, the graph of e to the x looks like this. So as you go in this direction towards negative infinity, you know, x is 10, x equals 100, x equals 1,000,000. The exponential function is getting really, the y values are getting really, really close to 0. Then likewise, if you have the limit as x goes to infinity of e to the negative x, you're plugging in values like negative or positive 10 will give you e to the negative 10, positive 100 will give you e to the negative 100. E to the negative 10 is 1 over e to the 10. E to the negative 100 is 1 over e to the 100. So you have 1 all over something that's getting really big. This thing will also go to 0. Okay, so these are special limits that are in the book. Let's go ahead and try to do some of these now and see how they behave for us. So number 19, you have the limit as x goes to infinity of 4 plus 3 over x. Okay, so what I was saying about the usual limit laws apply here. Here, if you could find the limit of 4 and as x goes to infinity, and then the limit of 3 over x as x goes to infinity, then the limit of the sum is equal to the sum of the limits. Okay, so you can write this as the limit as x goes to infinity of 4 plus the limit as x goes to infinity of 3 over x. Okay, so the limit of this thing as x goes to infinity, if you think in terms of sequences, you're going x is 10, it'll be 4, x is 100, it'll still be 4. It's always 4, it's a constant, right? So the limit is just going to be 4. The limit of a constant is just always a constant. Then this guy, if you're plugging in numbers like 10, 100, 1,000, a million, 3 over 10, 3 over 100, 3 over 1,000, it's getting really, really close to 0. In fact, that's that case I was going on about. If you have the limit of some fraction like this, in our case it's 1 over x, but if you in general you have 1 over x to the 10, 1 over x to the 100, whatever, it's going to equal 0 in the long run. Right? So this part, limit of 3 over x, is just going to be 0. In other words, 4 plus 0 is 4. 23. So we have the limit as x goes to infinity of x all over x squared minus 1. Okay, in this case, it's considered indeterminate. If you just look at the limit of x as x goes to infinity, that goes to infinity. If you look at the end behavior, it's just a diagonal line. As x goes to infinity, the y values are going to infinity. Okay? So this is infinity. X squared minus 1 is a parabola. So as x goes to infinity, that thing is going to go to infinity as well. So it's infinity over infinity. That's called an indeterminate form, like 0 over 0 before. So what we do is a bit of algebra, an algebraic trick. So the book will say, divide top and bottom by the high degree term. So in this case, 1 over x squared. And then we could rewrite this expression, will be the limit as x goes to infinity of x over x squared, all over x squared minus 1 over x squared. Simplifying, I'll have limit as x goes to infinity of 1 over x, all over 1 minus 1 over x squared. Okay. And then again, the limit laws apply. So the limit of the whole is equal to the limit of the parts, essentially, so long as the limit of the parts exist. And in this case, and the limit of the denominator is non-zero. So in this case, the limit of 1 over x we know is 0. Okay. That's kind of our presumption. The limit of basically any constant all over x to some number such that n is positive as x goes to either positive or negative infinity is going to be 0. It's this fact that we kind of use to evaluate these types of limits. So the limit of 1 is just 1. The limit of negative 1 over x squared, this part of it, is then, because of this law, also 0. So its form is really 0 over 1 minus 0, which is 0 over 1. 0 divided by 1 is 0. Okay. So its end behavior is y equals 0. It has an asymptote at y equals 0. And if you remember your pre-calculus, the degree of the numerator is 1. The degree of the denominator is 2. Therefore, the degree of the numerator is less than the degree of the denominator, and therefore, its horizontal asymptote is y equals 0. And that's exactly what we've just found. Okay. Its horizontal asymptote y equals 0. Okay, let's look at 27. So in this case, I have the limit as x goes to negative infinity of 2x plus 1 all over the square root of x squared minus x. Okay, this one, you are, I mean, if we did it numerically, we would be popping in values of x going to negative infinity. So negative 10, negative 100, negative 1,000. Right, so why do I even care? It's because I have, if I'm going to do this technique where I divide top and bottom by the high degree term, I'm actually dividing by something that's an absolute value. In particular here, this guy right here, the square root of x squared turns out to be the high degree term. Okay, so I have to multiply top and bottom by 1 all over the square root of x squared. 1 over the square root of x squared is not just simply 1 over x. It's 1 over the absolute value of x. And when you're going in this kind of direction, it turns out to be, well, negative x. Right? Okay, so you know, you want to be a little bit careful about what you're dividing by. Let's rewrite this part of it as we should. So it's 2x plus 1 times, not 1 over square root x squared, it's 1 over negative x. Because, look, square root of x squared, over here to the side, the square root of x squared is really the absolute value of x. And then the absolute value of x is negative x if x is less than 0. So that's why I'm saying, look, we're putting values like this into this equation if we were investigating it numerically. But what does that mean? That means I'm really working with this function when I plug it into these things, these 1 over square root x squared. So when I rewrite it, I'm doing 1 over negative x. It's this arm of my absolute value function. Okay, so downstairs then I can, you know, leave it as is. I have x squared all over x squared minus x over x squared. Okay. And then I can do the limit, I can reduce everything. So limit as x goes to negative infinity, 2x over negative x is negative 2, and then minus 1 over x, and then all over the square root of 1 minus 1 over x. And then using this law, this part will go to 0, this part will go to 0, and I'm left with negative 2 all over 1, which is just negative 2. It turns out there's an easier way to approach this problem than all of this business. Okay, so I just want to show you that. For example, number 23, I have the limit as x goes to infinity of x all over x squared minus 1. Whenever you have a ratio of polynomials, it turns out that its limit will be exactly the same as the limit of the ratio of their high degree terms. Okay, so this limit will be equal to the limit as x goes to infinity of x over x squared, which you can reduce to the limit as x goes to infinity of 1 over x. Okay. So we know from our general rule for limits that this limit is 0, so automatically it's 0. 27 then, we have the limit as x goes to negative infinity of 2x plus 1 all over the square root of x squared minus x. Again, you're saying the limit of this thing is equal to just the limit of the ratio of the high degree terms. And you could split up this radical for this type of work. So you have 2x all over the square root of x squared. Because my x values are going to negative infinity, I need to replace this thing with the appropriate arm of the absolute value function. So I had 2x over absolute value of x. In this direction, it's negative, right? So it would be the limit as x goes to negative infinity of 2x all over negative x. And then you could simplify this, it's just negative 2. Okay? That approach always works, and it's a lot quicker than all of this business with that the book tries to give you by dividing top and bottom by the high degree terms. So let's look at example 3 and do it kind of like in this new method, which I advise you to use. Okay, so part A, they want the limit as x goes to infinity of 2x plus 5 all over 3x squared plus 1. Okay. So that limit will be the same as the limit of this over that. So it's the limit as x goes to infinity of 2x all over 3x squared, which is the limit as x goes to infinity of 2 all over 3x. And then our rule, which I've lost, it goes to 0. Okay? So this will equal 0. Let's look at part B. The limit as x goes to infinity of 2x squared plus 5 all over 3x squared plus 1 is the same as the limit of these guys. So it's the same as the limit as x goes to infinity of 2x squared over 3x squared. And then the x squares divide out, and you just have the limit of 2/3. So you get 2/3. And then finally, part C, limit as x goes to infinity of 2x cubed plus 5 all over 3x squared plus 1 is the same as the limit of just this part. Right? That's the limit as x goes to infinity of 2x cubed all over x squared, which is the limit as x goes to infinity of 2x. So the line y equals 2x has a positive slope. It's going up like that. So as x goes to infinity, the y values will also go to infinity. Note, as x went to negative infinity, the y values would go to negative infinity. All right, then. That's the idea. Okay, so now we also have some infinite limits. We want to define those strictly. So that last limit we looked at, the limit as, where the heck did it go? I flipped it over. What did I do? This last limit is the kind we want to look at now, where they're going to infinity. We want to define strictly what does that mean. So section 4, infinite limits at infinity. First off, if the limit, so what does it mean? The limit as x goes to infinity of f of x equals infinity means that for any m value, there exists an n value. So we'll say any m greater than 0, there exists an n greater than 0 such that, as t for such that, if x is greater than n, then f of x will be greater than m. Okay? So for any m value you provide me, like 1,000,000, I can find an x value such that when I go beyond that x value, f of that x value will be greater than the number you gave me. Secondly then, the limit as x goes to infinity equals negative infinity of f of x equals negative infinity means basically the opposite direction. So it means that for any n value, m value less than 0, there exists an n value greater than 0 such that if we go beyond that n value, then f of x will be less than the m value. Okay, so that happens a lot with our polynomial characters. Let's look at 31, our rational functions. I mean, obviously polynomials will always either go to positive or negative infinity. For example, the limit of negative 3x cubed plus 2x plus 1 as x goes to positive infinity. You could think about what the curve looks like, right? So the leading coefficient is negative, it's an odd degree, so it's going to have this type behavior. In other words, it's going to negative infinity as x goes to infinity. But that's not 31. Let's look at 31. They want to know the limit of x plus 1 all over x squared plus 1 to the 1/3 power as x goes to infinity. You can rewrite this by kind of just grabbing this portion and making a ratio. So this would be the limit as x goes to infinity of x all over x to the 2/3, right, which equals the limit as x goes to infinity of x to the 1 minus 2/3, in other words, x to the 1/3. And if you think about the cube root function, as x goes to infinity, the cube root is also going to go to infinity. So this will be infinity. In other words, when you can always pull this trick where you're just picking off the high degree terms of your polynomials and considering those. I mean, even here, that's what we did, right? We looked at the sign of the thing, and then the degree tells us whether it's going down or going up in the end. Let's look at an actual example, an application on learning theory, which is something that here at Tri-C our professors are interested in, because we are a teaching college. Learning theory. They give us a function which describes, I believe, the rate that you, let me look. Okay, so this is 4.5, number 95. Learning theory. In a group project on learning theory, a mathematical model for the proportion p of correct responses after n trials was found to be p of n equaling 0.83 all over 1 plus e to the negative 0.2n. We call this model a logistic model later on, and you'll see that in differential equations. Okay, so part A, find the limiting proportion of correct responses as n approaches infinity. So again, P of n is the number of correct responses after n trials. So let's say a person had an infinite number of trials. What would be the best case scenario? Okay, in other words, they're asking you to take the limit of P of n as n goes to infinity. So what is that? Well, again, so long as the limits of the pieces exist and the limit of the entire denominator is not 0, the limit of P of n will just be the limit of the individual pieces. Okay, so the limit of this part is just 0.83. The limit of a constant is a constant. The limit of 1 is just 1. So it really comes down to the limit of this thingamajig. So the limit as n goes to infinity of e to the negative 0.2n. This thing is the same as the limit as n goes to infinity of 1 all over e to the 0.2n. This thing is a lot like our limits, limit as n goes to infinity of something like 1 all over x to the nth power, right? Or rather 1 all over n to some variable. So it's more like the limit. Let me rewrite it as x goes to infinity of 1 all over x to the 5th or something like that. We know this goes to 0, and it's because that denominator is getting really, really big if you look at the numerical analysis, right? So if you're plugging in 10, this output would be 1 over 10 to the 5th. If you put in 100, this output would be 1 over 100 to the 5th. This behavior is almost exactly like this behavior. Right, so if you did a numerical analysis as n goes to infinity, and we have n and then our sort of output function 1 all over e to the 0.2n, As n goes, we have 10, so that would be 1 all over e to the 2. At 100, that would be 1 all over e to the 20. And it's the same kind of phenomena going on, right? If you have 1,000, it's 1 all over e to the 200. Okay? So you're getting something like 1 all over something huge. In other words, this thing is going to 0. This part of it, this part is going to 0. Okay? So at the end, the limit of this thing will just be the numerator. It's 0.83 over 1 plus 0, which is just 0.83. In other words, in the long run, you'd expect somebody with an infinite number of trials to get 83 and 83%. Okay. Okay. Part B, find the rate at which P is changing after n equals 3 trials and n equals 10 trials. Okay. When n is 3 and n is 10. So the rate at which P of n is changing is basically just the derivative. So they want you to find the derivative and then evaluate the derivative at 3 and 10. So to find the derivative, let's first rewrite this expression, P of n as 0.83 times 1 plus e to the negative 0.2n, all raised to the negative 1. Okay, so to take the derivative, I'm going to have to do a power rule and then a chain rule. So the power rule on this will give me negative 0.83 times 1 plus e to the negative 0.2n to the negative 2. And then the chain rule part, the derivative of 1 is 0. The derivative of e to the negative 0.2n is e to the negative 0.2n right back. And then times the derivative of the exponent, which would be negative 0.2. Okay, so cleaning that up a bit, let's see what I get. I have 0.166 e to the negative 0.2n all over 1 plus e to the negative 0.2n squared. And then I just have to plop in n equals 3 and n equals 10. So when p prime of 3, if I go with my calculator really quick, is 0.038, and then p prime of 10, after 10 trials, 0.017. So in the beginning, there's a higher rate of change. And I think that's true in general for beginning levels of math. You're going to see a higher learning rate than as you get into it more and more in depth. So your learning rate will probably change or get slower the longer you're doing math. Maybe that's a good thing, maybe it's a bad thing, I don't know. Okay, but it's something, as an educator, I'd be very interested in knowing so I could take advantage of that fact to become a better educator. Okay, so there's that. That'll do it for this section. Thanks for watching.